Hello, everyone. We are excited to share our CVPR 2026 paper titled Rethinking Concept Bottleneck Models from Pitfalls to Solutions. Concept bottleneck models, or CBMs, aim to make neural network predictions interpretable by forcing predictions to pass through human-understandable concepts. Recently, many CBMs have been built using pre-trained vision language models, enabling scalable concept extraction without manual annotation. However, current VLM-based CBMs still suffer from several important limitations. First, CBMs may achieve high accuracy even when the selected concept set is largely irrelevant to the dataset, suggesting that concepts can still encode latent correlations with class labels. Second, we uncover the linearity problem. When both the concept encoder and classifier are linear, the model degenerates into a standard linear classifier and effectively ignores the concept bottleneck. Third, CBMs often exhibit a performance gap compared to opaque classifiers. And finally, prior work lacks a systematic study of how backbone and VLM choices affect CBM behavior. Here, we illustrate the linearity problem. Even with random strings or irrelevant Roman law terminology as concepts, linear CBMs still achieve high classification accuracy. For example, on the ImageNet 100 dataset, a linear CBM can achieve over 85% accuracy using entirely irrelevant concept sets. To address these limitations, we introduce CBM-Suite. First, we evaluate concept relevance using an entropy-based goodness of concepts metric before training. Given an input image xi, we compute concept activation ci using the cosine similarity between image and text embeddings extracted from a vision language model. We observe that relevant concept sets produce more concentrated activation distributions, leading to lower entropy, while irrelevant concepts tend to follow a more diffuse, approximately normal distribution. Based on this observation, we define a quantitative measure of concept quality at both the dataset level, which we call task agnostic, and at the class level, which we call task specific. Here, we focus on the task-agnostic goodness of concepts metric. We first convert the concept activations into a probability distribution using softmax, and then compute the entropy of this distribution. Next, we train a nonlinear concept encoder to ensure predictions genuinely depend on concepts. We train this module using a mean-squared error loss. This nonlinearity is critical as it prevents the encoder from collapsing into a purely linear transformation. We then apply knowledge distillation to recover predictive performance while preserving interpretability. The teacher model is a simple linear probe trained directly on image embeddings using cross-entropy loss. We then train the CBM classifier using a combined objective consisting of 3 terms, standard cross-entropy loss, elastic net regularization, and a knowledge distillation loss that aligns CBM's predictions with the teacher logits. Finally, we explore the modular structure of CBMs by evaluating different combinations of vision backbones and VLMs. This analysis helps us understand how these design choices affect CBM performance and behavior. Here, we present the proposed goodness of concepts metric across concept sets and datasets. Relevant concept sets yield the lowest entropy, indicating more concentrated and structured activations. We compare CBMs trained with relevant and irrelevant concept sets, varying only the concept encoder, linear versus nonlinear. Linear CBMs are largely insensitive to concept quality, while nonlinear CBMs show clear performance drops with irrelevant concepts, indicating stronger reliance on the concept bottleneck. Nonlinear models also exhibit higher variance across runs, as reflected in the error bars over 10 random initializations. To evaluate the effect of teacher-guided training, we compare Oracle, vanilla CBM, and distilled CBM. The distilled CBM uses the full CBM-Suite objective, while the vanilla CBM excludes distillation, and Oracle is a linear probe on backbone features. Our results show that knowledge distillation consistently improves CBM performance and helps narrow the gap to the Oracle baseline. We evaluate multiple vision backbone and VLM combinations on ImageNet 100. Performance varies more across backbones than VLMs, highlighting the importance of representation strength. Perception encoder achieves the best overall results, while SIGLIP performs best among most VLM settings. In summary, we identify key limitations in recent VLM-based CBMs and introduce CBM-Suite to improve their reliability and interpretability. Our results highlight the importance of concept quality, nonlinear encoding, knowledge distillation, and representation choices in trustworthy CBM design. Thank you for listening.